Today, we are summarizing PyVision-RL, forging open agentic vision models via RL. Here are the key insights.
Right, so to start, multimodal agents trained with reinforcement learning often suffer from what's called interaction collapse. They basically get lazy and stop using tools or engaging in multi-turn reasoning.
Yeah, and on top of that, current video reasoning models waste massive amounts of tokens through uniform frame sampling. So the solution proposed here is PyVision-RL.
It introduces a framework using Python as a primitive tool for dynamic reasoning, and it stabilizes the training using an accumulative tool reward that explicitly incentivizes multi-turn code execution.
Along with a novel oversampling-filtering-ranking rollout strategy. And for video, there's this massive breakthrough they call on-demand context construction.
Exactly. The video is loaded only into the Python runtime. The model then writes code to dynamically sample just the task-relevant frames.
And the results are wild. It achieves state-of-the-art performance on benchmarks like VStar and Waymath.
But more impressively, PyVision-Video hits 44% accuracy on VSI bench using an average of just 5,000 visual tokens per sample.
Compared to Qwen 2.5 VL7B's 38% accuracy, which requires a massive 45,000 tokens.
It's a huge leap in efficiency.
Welcome to AI Paper Podcasts. If you are an AI researcher or an ML engineer who is currently wrestling with agentic workflows or, trying to scale test time compute in multimodal models, you know exactly how painful these bottlenecks are.
Oh yeah, the token costs alone will keep you up at night.
Definitely. So we are stripping this paper down to the studs today to see how it ticks. This is a deep dive into the source material that you won't want to miss.
The mission for our exploration today is getting into the weeds of how these researchers manipulated RL algorithms, specifically group relative policy optimization, or GRPO, to prevent that mode collapse we mentioned.
Right. Yeah.
We're going to look at why treating a Python interpreter as a visual primitive completely changes the architecture of an agent.
I think we should probably set the stage first by looking at the current landscape of tool use in vision models.
Good idea.
Because most of the open-weight models you might pull off Hugging Face today, they rely on static tool sets.
Yeah, highly rigid setups.
Right. You give the model a predefined set of tools, maybe a specific cropping function or a manual zoom function that's exposed via an API. You hand over a literal coordinate box and just sort of hope the model uses it right.
And that inflexibility completely bottlenecks scaling. I mean, every new task requires a massive amount of task-dependent engineering.
You're writing a new API endpoint for every single action.
Exactly. Contrast that static approach with dynamic tooling, which totally flips the paradigm. Instead of giving the model a rigid set of buttons to press, you give it an empty workspace.
A Python interpreter.
Yes. You treat Python itself as the primitive tool. The model synthesizes task-specific operations on the fly. It can import libraries like NumPy or Matplotlib.
Write loops, extract specific data arrays.
Right, and manipulate the image however it sees fit. It is infinitely more expressive than a static API.
The theory sounds perfect, but that brings us to the core training challenge the researchers identify, the interaction collapse.
The fundamental RL bottleneck for agents.
Yeah, you take these highly capable models, you fine-tune them with reinforcement learning to use these tools, and suddenly they just stop tracking.
They get lazy. They converge to short, low-interaction behaviors.
Why does that happen, though?
The model essentially learns that doing less is a safer, mathematically optimal way to secure a baseline reward. Or it simply gets confused by the compounding complexity of its own code trajectories.
Like if it writes a bug on turn 1, turn 2 is doomed.
Exactly.
Yeah.
So it learns to just guess the answer immediately to avoid the penalty of a crash.
That makes sense.
Prior research in the field assumed that test-time interaction scaling, which works so beautifully in text-only models like OpenAI's O1 or DeepSeek R1, inherently didn't translate to vision.
But this paper argues otherwise.
Right. They make the argument that interaction collapse is not an inherent weakness of multimodal agents at all. It's just a symptom of insufficient training incentives and highly unstable rollout selection during the RL phase.
Okay, so if the model is getting lazy because the reward structure is broken, how do we fix the incentive? Because I know if I tell a model it gets bonus points just for writing code, it is going to start writing endless print hello world loops to farm those rewards.
Reward hacking. Yeah, the design of their accumulative tool reward prevents exactly that.
How does the math work there?
Normally, in reinforcement learning, your reward function heavily indexes on just getting the final answer correct. We can call that base reward R at C.
And if you just reward the final answer, the model finds the shortest path.
Or it just hallucinates a guess, completely skipping the tools. So the researchers added an explicit mathematical incentive, an additional reward of 0.1 multiplied by the number of tool calls the model makes.
Which brings us right back to the endless loop problem, doesn't it?
That is where they introduce a crucial, non-negotiable condition. That accumulative tool reward is only multiplied and added to the final score if the final answer is actually correct.
Oh, wow.
Yeah, the mathematical formulation includes an indicator function that zeroes out the entire tool reward if the final answer is wrong.
So it stops the model from spamming infinite, useless loops, but heavily rewards sustained multi-turn reasoning that actually leads to the right conclusion.
Precisely. Looking at the ablation studies in the paper, without this accumulative tool reward, the average number of tool calls rapidly drops and flatlines at a very low number during the early epochs of training.
But with it,
the tool usage steadily climbs. The agent learns that thinking deeper and longer actually pays off.
Okay, but training an agent that writes arbitrary Python code to interact with an environment is pure chaos. You're dealing with timeouts, broken code, syntax errors, rendering failures.
It's messy.
If the RL algorithm is trying to learn from that noise during rollout generation, I imagine the gradients just explode.
They absolutely would. Managing that chaos requires a brilliant pipeline for oversampling, filtering, and ranking. They had to modify vanilla group relative policy optimization, or GRPO, to handle the realities of software agents.
So step one is oversampling, right?
Yeah, they generate a massive batch of rollouts for a single prompt, far more than they actually intend to train on.
And then step two is the online filtering.
They automatically dump any broken trajectories where the code crashed or the agent failed to render an image properly. They also filter out rollout groups that have zero reward variance.
Because if every rollout in a group gets the exact same reward, the algorithm just freezes up. If everyone fails or everyone succeeds perfectly, there's no delta to learn from.
Which means it's literally wasted compute. You need a gradient. Step 3 is the real innovation, though. Standard deviation sorting.
Okay, break that down for me.
They sort the surviving rollout groups by their reward standard deviation, and they only keep the top-ranked ones for the actual training step.
Using standard deviation as a sorting metric feels highly specific. Why not just take the ones with the highest overall scores?
Because high standard deviation acts as a proxy for sample difficulty. It creates an automatic curriculum learning environment.
Ah, I see.
If a group has high reward variance, it means the model got it right in some rollouts and completely wrong in others. The policy is currently struggling right at the boundary of its capabilities for that specific prompt.
So by sorting and training strictly on these high variance groups, they force the model to learn from moderately difficult samples.
Exactly. Those samples provide the most informative gradient signals, rather than wasting time on trivial successes or impossible failures.
Speaking of gradients, I noticed a highly technical tweak in the paper regarding GRPO's advantage estimation. They entirely removed the standard deviation normalization term in the intragroup advantage computation.
Yes, that is a huge detail.
Why mess with the core math of GRPO like that?
Imagine grading a test on a curve. If one student writes a brilliant, highly efficient one-line mathematical proof, and another student writes a messy, meandering three-page proof.
But both ultimately arrive at the correct answer.
Right. A standard grading curve might actually penalize the brilliant student for being a statistical outlier. Standard GRPO does exactly this to efficient code.
How so?
You normalize the advantages within a group. Because of how the accumulative tool reward works, a highly elegant solution with fewer tool calls will have a slightly lower absolute reward than a longer correct solution that used more tools.
Because it didn't rack up the 0.1 bonus as many times.
Exactly. So when you normalize that group by standard deviation, that slightly lower but still totally correct and highly efficient rollout can actually get assigned a mathematically negative advantage.
Wow. So the algorithm was actively penalizing correct trajectories just because they were relatively shorter than others in the batch.
By removing that standard deviation normalization and relying purely on their ranking strategy to handle variance, they threw out the grading curve.
And that stabilized things.
They massively stabilized the training dynamics. The paper reports a nearly 5% performance jump on the V-star benchmark simply from deleting that single normalization term.
That is incredible. Dynamic tooling clearly fixes the reasoning bottleneck for static images. But earlier, the numbers for video processing were absolutely staggering.
The video application is where this really shines.
Right now, if you take a frontier model like Qwen 2.5 VL and ask it a question about a minute-long video, it processes it by blindly sampling frames.
Uniform frame sampling is the industry standard, and it is horribly inefficient. The model simply grabs frames at a set rate, say 1 frame per second or maybe 64 frames total.
And it dumps every single one of them into the context window.
It costs up to 45,000 tokens per video for Qwen 2.5 VL to reach its peak accuracy.
Not only is that computationally expensive, driving up inference costs, but it severely dilutes the model's attention mechanism.
Exactly. If you're asking a specific question about a tiny object sitting on a table in frame 100, dumping frame 2000 into the context window just adds visual noise.
Which brings us to the PyVision-Video solution. They call it on-demand context construction.
This is brilliant. The video file does not go into the LLM's context window at all.
Wait, not at all?
Not at all.
Okay.
It is only loaded into the Python runtime environment.
It is a beautiful architectural choice.
The multimodal LLM relies on its system prompt to understand that it has access to a video variable residing in the Python runtime.
So it then writes Python code using standard libraries like Decord or Matplotlib to query the video.
Yes. It selectively samples specific frames based on its own internal reasoning and plots them. The model only sees the visual tokens for the frames it explicitly writes code to fetch and render as execution outputs.
It's essentially replicating human behavior. You don't watch a video by printing out every single frame, laying them all out on a massive table, and staring at them simultaneously.
That'd be absurd.
You scrub. You skip to the relevant timestamp, you pause, and you look closely at the part that matters.
And this active agentic frame fetching strategy causes the average token consumption to absolutely plummet. PyVision-Video drops the average token consumption to roughly 5,000 tokens per sample.
Down from that 45,000 token baseline.
Because the model is only looking at exactly what it needs to solve the prompt, the signal-to-noise ratio improves, and the accuracy actually goes up.
You mentioned PyVision-Video hit 44% on VSI Bench, which tests spatial reasoning in video compared to the baseline's 38%.
It completely redefines the performance efficiency trade-off for spatial and temporal reasoning.
I really want to walk through some of the specific case studies from the paper's benchmarks. They break down actual output logs from TI Bench and VSI Bench, and it makes this abstract dynamic tooling very concrete.
Oh, the logs are fascinating.
Let's look at the color VQA test. The model is given a static image showing 3 pink circles side by side. The prompt asks which circle has the darkest color.
Right, so a standard vision model might just guess. Or it might get confused by subtle compression artifacts or monitor calibration issues.
But PyVision-Image takes an engineering approach.
It writes a Python script. First, it uses Matplotlib to crop and zoom in on the image. Then, it uses NumPy to extract the RGB channels as distinct mathematical arrays.
And finally, it plots a statistical histogram of the pixel intensities for all 3 color channels.
It bypasses the visual ambiguity entirely and just does the math on the raw pixels.
It looks at the resulting histograms, observes that the distributions are mathematically identical across all 3 circles, and uses that hard data to definitively conclude and prove that the circles are the exact same shade.
It didn't just look at the image, it measured the underlying data structure.
Case 2 is the rotation game. The agent is given an image of a street, but the image is heavily tilted. The prompt asks for the exact clockwise degree rotation required to fix it and restore the original horizon orientation.
Here, the agent engages in explicit hypothesis testing. It looks at the initial image and reasons that the horizon is tilted counterclockwise.
It hypothesizes that a 315-degree clockwise rotation might fix it, which is mathematically equivalent to a 45-degree counterclockwise correction.
But rather than just outputting the number and hoping for the best, it writes a Python script. Image.rotate 315.
It executes the code, plots the newly rotated image, visually confirms that the street, buildings, and sky are now perfectly level in the new output, and then confidently locks in the answer.
It is a closed-loop verification system.
The third case study is a video special measurement task from VSI Bench, and it really shows off the on-demand context construction. The prompt asks for the physical length of a table in a room in centimeters, based entirely on a raw video file.
This requires intense compositional reasoning. Model starts by writing code to sample frames at wide intervals, say every 300 frames. It scrubs through the video to find a clear, unobstructed view of the table.
It identifies frame 100 as having the best angle.
Now, it needs a reference scale, because pixels do not equal centimeters. It spots a standard dining chair sitting next to the table.
So it writes a new block of code to overlay a Cartesian coordinate grid on the image. Using that grid, it measures the chair at approximately 100 pixels wide.
Then it pulls in real-world knowledge from its pre-training, assuming a standard dining chair is about 42 centimeters wide.
That is wild. It calculates a precise pixel to centimeter ratio, 0.42 centimeters per pixel.
It then uses that exact same grid to measure the table's length in the image, determining it is 640 pixels long.
It multiplies the two values and calculates a final physical length of approximately 268 centimeters.
It navigated a video file, found the optimal frame, established a relative scale using external knowledge, applied a geometric grid overlay, and calculated a physical dimension.
That is a massive operational leap over standard visual question answering.
The benchmarks absolutely back up how powerful this methodology is. Both the baseline and the new model are built on Qwen 2.5 VL 7BD. PyVision-Image dominates the leaderboards.
It beats a dynamic tooling model called DeepEye's V2 by 6.9% on the V-Star visual search benchmark.
And by an impressive 9.6% on WeMath, which specifically tests complex mathematical reasoning over visual inputs.
The ablation studies in the paper prove exactly why these models are winning. They experimented extensively with the maximum turn budget.
That is the hard cap programmed into the while loop for how many back-and-forth tool interactions the agent is allowed to make before it is forced to output a final answer.
And they found that increasing the budget from 2 turns to 4 turns greatly increased the performance ceiling.
Especially in the later stages of reinforcement learning. It proves empirically that deep multi-step thinking is an absolute requirement for these complex spatial and mathematical tasks.
Giving the model the computational space to think, combined with the reward structure to encourage it, unlocks capabilities that single-step reactive models simply cannot access.
But we do need to talk about the risks. Deploying an automated software engineer that writes and executes arbitrary code comes with serious operational realities.
Yeah, the safety implications highlighted in the paper's impact statement cannot be ignored if you are building these pipelines.
Giving a large language model raw, programmatic access to a Python interpreter means it inherently has potential access to the host file system.
If the model can import standard OS libraries, it can read sensitive files, delete directories, or execute system-level commands.
The researchers explicitly warned that deploying open agentic models like PyVision requires severe, uncompromising sandboxing. You are not just deploying a text-based chatbot, you are deploying an agent that takes actions.
Strict isolation, containerized virtualization, and hard execution limits on CPU and memory usage are absolutely mandatory to prevent catastrophic system failures or security breaches.
It's a fundamental paradigm shift in how we build multimodal systems. We are moving away from models that passively consume static arrays of visual inputs
to active agents that manipulate, query, and mathematically dissect their visual environments using code. They are actively investigating the world rather than just looking at it.
And the implications of this architecture leave us with a truly provocative thought. If these open-weight models can act dynamically on static videos and images using Python, reducing a 45,000 token video to a 5,000 token targeted query.
What happens when we hook this exact RL framework up to live, continuous robotic camera feeds?
Exactly. The biggest bottlenecks in real-time physical robotics right now are latency and context window exhaustion. A robot processing a live feed cannot afford to dump uniform frames into an LLM every single second.
But on-demand context construction might be the skeleton key.
Imagine a robotic agent that does not process every frame of its camera feed, but instead dynamically runs lightweight Python queries to fetch only the visual data it needs, exactly when it needs it, to navigate a room or manipulate an object.
This paper could very well be the foundational blueprint for scalable real-time robotic vision.
It really could.
That is an incredible concept to mull over as you build out your own agentic pipelines. Thank you for tuning in to this deep dive into the source material on AI paper podcasts. We highly encourage you to check out the open source code, the SFT datasets, and the models linked in the paper's repository. Stay curious, and we will catch you on the next one.